Welcome to the video on point and rotational symmetry. Remember, if at any time during this video I say something that doesn't make sense, please rewind and replay and listen to the presentation again. If it still doesn't make sense, make a note in the margin so that you can remember to ask about it the next time that you come to class. Point symmetry, kind of a fancy definition, which really isn't all that complicated when we slow down and think about it in simple terms. It says point symmetry exists when a figure is built around a single point, and that point is called the center of the figure. In other words, for each and every point in the figure, there is another point found directly opposite it on the other side of the center. To determine whether or not a figure has point symmetry, turn it upside down and see if it looks unchanged. See if it looks the same. If the figure looks the same upside down as it did right side up, we say that the figure has point symmetry. All right, so down underneath here it says circle the shapes that have point symmetry. So what you're going to do here is you're going to take your packet, you're going to flip it upside down, and you're going to see if the figure remains unchanged after flipping it upside down. So this first one, the word noon, go ahead and take your packet, flip your packet upside down. Does it still say the word noon? Yes, since it's the same upside down as it was right side up, that figure has point symmetry. The triangle, go ahead and take that one and tip it upside down. Now, when we tip that guy upside down, the triangle's pointing downwards instead of upwards, so he does not have point symmetry. All right, the smiley face. When we turn him upside down, he becomes a frowny. Since he is not exactly the same upside down as he was right side up, he does not have point symmetry. And the jack, go ahead and flip the jack upside down. When you turn him upside down, is he exactly the same as he was right side up? Yes, so he, like the word noon, does have point symmetry. So that's the whole idea behind point symmetry. Rotational symmetry, same idea, but instead of flipping it 180 degrees, instead of rotating that paper 180 degrees, now we're going to see if there's any number of degrees between 0 and 360 where it will look the same as it did originally. So in other words, where it will coincide with itself. It says here that we exclude the angles of 0 degrees and 360 degrees since nothing very exciting happens. 0 degrees means we're not going to rotate at all. 360 degrees means we would do one complete rotation, which of course would bring it back onto itself. So let's go ahead, and I think this table is going to be a little bit easier to fill out if we answered the bottom question first. So first of all, does the figure have rotational symmetry? In other words, can we rotate at some number of degrees that's greater than 0 but less than 360 where it will appear exactly the same as when we started? For this octagon, the answer to that is yes. And as far as the degrees of rotation are concerned, the easiest one probably to predict here is 180 degrees. If we flip him upside down, he's going to be unchanged. But are there any others besides 180 degrees? You might say, Mrs. McCann, if I took and rotated my paper a quarter turn, well, a quarter of 360 degrees, an entire turn would be 90 degrees. That octagon would also appear unchanged. And I would have to agree with you. You're absolutely right. But what if I took and I rotated and put that red line segment right where the blue line segment is? That's not quite a 90-degree turn, but in fact, that's a 45-degree turn. And that too will result in the figure coinciding with itself, with it remaining unchanged. So the smallest number of degrees that we can rotate this octagon to get the figure on top of itself again is 45 degrees. We can also do all multiples of 45 degrees up to but not including 360 degrees. So 90 degrees would work, 135 degrees would work, 180 degrees would work, 225, 270, 315, and then another 45 would put us back at 360, and we don't want to include that. You might say, well, how's a simple way I could find that if I didn't see this 45 degrees right off the bat? Well, 360 degrees in a complete rotation or a complete revolution, this octagon has 8 sides. So 360 divided by 8. If that had been a triangle, I would have taken the 360, divided it by 3, because a triangle has 3 sides. If it had been a square, I would have taken the 360, divided it by 4. And kind of an important note here is that this figure, whatever it is, this polygon, has to be a regular polygon, meaning all of its sides have to be congruent in order for this to work. All right, so that's the deal with the octagon. He's the most complicated figure in this whole chart. So we've kind of got the hardest one knocked off right from the very beginning. The trapezoid, this next guy over here, if I take and I turn him 180 degrees, the longer side is going to be at the bottom, shorter side going to be at the top. If I turn them 90 degrees, my parallel sides are going to be the left and right, and it's not going to match up with how we started. So this guy has no rotational symmetry, and because he has no rotational symmetry, he has no degrees of rotation. So that would be for the trapezoid. These guys here all go for my octagon. This arrow, my next figure, I could flip him upside down. He has not only rotational symmetry, but also point symmetry. So he does also have rotational symmetry. And if I flip him 180 degrees, he's going to be exactly the same as he started, making his only degrees of rotation 180. And as far as the letter H, he behaves very similarly to that arrow. Yes, he has rotational symmetry, and his degrees of rotation are also 180. All right, let's go ahead and flip up to the top of the next page, and we're going to talk a little bit about point reflection. A point reflection does exactly what it sounds like. It takes and it reflects each point on a given figure through a point. So whereas for a line reflection, we reflect it across or over or through a line, now we're going to reflect through a single point. Here's the real big key piece of information that you have to know about a point reflection. When a line segment is drawn connecting any point in the original figure with its corresponding point in the image, that point of reflection becomes the midpoint of the line segment that connects the two. So here's what I'm talking about. If I go name this triangle X, Y, Z, then when point X is reflected through point A, its image down here is X prime is going to be located in such a spot that the distance between points X and A is equal to the distance between points A and X. Likewise, if I go to reflect point Y through point A, I'm going to do so in a way that's going to make point A the midpoint of the line segment that joins Y in its image, Y prime. So these guys would be congruent to each other. And similarly, if I go to reflect point Z through point A, I'm going to do so in such a fashion that point A becomes the midpoint of the line segment which connects Z in its image, Z prime. So the notation here that we might want to use, or that we will want to use for a point reflection, I'm going to use lowercase r for reflection of point X. All right, I'm going to back up here just a minute and talk a little bit about notation. I'm going to use a lowercase r to represent reflection, just like when we did line reflection. Reflection through point A of point X is X prime. So just like when we did line reflections, that small lowercase r represents reflection. Don't confuse that with the capital R for rotation. The subscript is the point that we're reflecting through. In parentheses goes the point we're reflecting. And X prime, of course, is the image of point X under that point reflection. All right, let's go take an example of look at an example of what this would look like in the coordinate plane. It says we're going to start with triangle ABC with those coordinates. Graph and state the coordinates of triangle A prime, B prime, C prime, which is going to be the image of the original triangle after reflecting it through the origin. So I'm going to go ahead and I'm going to start with triangle ABC, and I'll go plot those points first of all. Now that I see where point A ends up or point C ends up, I'm going to change the way I label that just a little bit. So there's my triangle that I want to reflect through the origin. The origin is a point. Its coordinates are 0, 0. So in other words, just like every other transformation we've done when we've transformed a whole figure, we're going to transform one point at a time. Once we figure out where all those points end up, we'll use our straight edge to connect them. So I need to find a point on the other side of the origin such that the origin is the midpoint between point A and its image. So if I put point A prime right there, the origin now is the midpoint of those two guys. If I go to the left one and down 2, left one and down 2, the origin is now the midpoint between A and A prime, and I've successfully now reflected point A through the origin. I'm going to go repeat those steps for each and every one of these points in my figure. So point B, I have to go to the left 3 and down 4. To find point B prime, I'm going to go to the left 3 and down 4. And there's point B prime. So again, the point I'm reflecting through, the origin, becomes the midpoint between B and its image, B prime. And for C prime, I need to go to the left 1, down 5. So to find its image, I'm going to go to the left 1, down 5. And again, I'm just going to double check and make sure that that point that I'm trying to reflect through, the origin, is the midpoint between C and C prime. And it is, so I think I've done a good job here. And it says graph and state the coordinates. So not only do I have to draw the graph, but I need to make sure that I read and follow directions and state the coordinates. So point A prime has coordinates -1, -2. Point B prime has coordinates -3, -4. Point C prime has coordinates -1, -5. And if you take just a minute to go up and pay a little bit of attention to what the original coordinates were and what the new coordinates are after a reflection through the origin, notice that that reflection in the origin has taken each one of the coordinates and its image has opposites. So it takes any point whose coordinates are x, y, and under a reflection in the origin, the new coordinates are going to be the opposite of what the original x was and the opposite of what the original y was. All right, the last example has to do with some more point reflections, but I think we're going to call it a day there. As always, thank you for the gift of your time. And if you have any questions, please do make sure that you jot them down so that when you come back to class, we can make sure that I address them.